So 10.1 then, decided on how.
I will talk about problem 1, but I will put some lemma in problem 1 and it can solve the problem 2 simultaneously.
Okay, very well.
First, we know some facts. In some n-dimensional Euclidean space, if we have some lattice denoted by omega, and if we have some set, how do you say, some set U is surrounded by is a finite volume space, and then the intersection.
Mm-hmm.
It is clear. Right.
It's clear from here. That's. This is a lattice.
And for the lattice, we don't know the dimension. I mean, it can be finite or infinite dimension.
No, it's inside Rn.
Okay, it's just.
So it is n-dimensional, yes.
Okay.
Is it clear? Yes, I think it's clear. It's the number of this. And the second, I want to prove some.
Yes, I think you can just surround every point of your lattice with some, I don't know, sphere of fixed volume, such that no other point is inside. And of course, if you have infinite number of points inside U, then you have infinite number of the spheres inside U. Which is of course a contradiction, right?
And what I want to prove for this problem 1, I want to prove this is inside some set element, and then you take inside some V, and you take this is less than infinity, so this is less than infinity.
Okay.
Sort of.
So you will give us some V such that. Mm-hmm.
And let's record the definition.
In the first fact, we need some more requirement for this finite value things, maybe. Because if we have something like
Should be compact, right?
yeah, or the open set. Or
Compact.
if we have a lattice and we just take the line, and the line is with no value.
Yes.
And then we get.
No,
I
I just in Rn this means you the integral with respect to the V.
But still, it's still the.
Okay, I see. Yes. The final answer is also.
It should be compact. That's it.
Yes. Of course. The final. This is definition. This is because in the previous lecture seminars we explained why we can use the simple.
I'm sorry. What is the subscript of P?
P lambda.
And what is the dependence on lambda on the right? I think you should change lambda on the right to mu, and then also write mu less or equal than lambda.
Lambda is fixed, but
Yes.
Mhm. This is better, and also maybe you would like to have mu less or equal than lambda.
Yes.
Well, inside the set. Okay, yes. Mhm. Okay.
And
Okay.
and this is the definition of this one.
Mhm.
And I want to first prove that these things is some subset of some space. And for example, this is our origin, and this is, I just read the picture of the two-dimensional things, and for the higher dimensional things, it's the same. I want to say that this area just C plus this the closure of C plus is inside that area. It's something like the convex combination, not exactly the convex combination, but
So this is some statement that you would like to prove that C plus is inside
this is clear because you have some polarization, and you cannot have some, for example, some vector outside this area. Well, not satisfactory.
What is exactly the set that can you write in formulas that you highlight on this picture? So this is set of all lambdas.
This is just some.
linear combination of alpha.
Yes, so in formulas should be like that. Maybe C tilde, I don't know. This is all lambdas C I alpha I from 1 to R,
Yes.
such that C I greater or equal than 0. This is what it is, right?
Yes.
Okay. And so you say that C plus bar is inside C tilde. Why is that?
Let's just prove. Because if the root here is have all positive
Yes. So if you take
Okay,
alpha,
okay.
decompose it in alpha i's, it has positive coefficients. Right.
I'm sorry, can you please repeat?
this is the thing we want to prove.
Yes.
Yeah.
And this is the definition of this. And that is the definition.
Yeah. Nothing else was said. We're just now trying to.
Because I think that's something similar to do in problem 2 as well.
Yes, it's how actually mentioned that there's some relation to problem 2. I don't know if.
This is clear if we choose some element outside this C tilde, and then this C tilde cannot satisfy this. If we just things how to say?
I was trying to prove this problem this way, and I didn't succeed. So I couldn't find like a clear explanation. Of course, what you're saying is true, should be true, but it's not clear. It's not clear why, right? So if you try to imagine pictures inside your head, yeah, it should be true. But how to prove that?
How you mean how to prove?
How to prove that C plus bar is inside C tilde? So I don't know. So the solution that I can explain is a bit different. So, but I don't know if you tell me, then it will be cool.
I think is maybe I didn't write the explicit proof. I think it can be some.
So, did you solve
we
this?
solved it together, but I almost
So what-
forget. Yeah.
Uh-huh.
I was thinking.
Yes, maybe for
Okay. So
we
you.
can choose.
Mhm.
We can choose some.
I don't know, if you take something outside of C tilde, you would like it to be outside. You would like to choose some, find some alpha, some positive root such that lambda with this root is negative, right? That's what you would like.
Yeah, okay.
But yeah, this I don't know. But okay, so if we are stuck, well, maybe so if you have this, then what's the argument after
The
that?
argument is quite clear since you write this.
Mm-hmm.
This alpha I are the symbols.
Mm-hmm.
Right. And you can see mu is exactly lambda minus AI alpha. Mu is fixed. And look at this alpha as symbols is exactly parallel to the root we wrote here. And the things will, the intersection of, the boundary of, if this is the past width, then it has something like this. And I mean this, the intersection of this part, and this will be a finite volume.
Okay, can you write this in formulas? So intersection of P lambda and C tilde, right? This is what you would like to do. And you would like to say that intersection of P lambda and C tilde is finite, right?
Yes.
And then intersection of P lambda, can you write down the formula for this set? So what I would like to see, to make it completely clear, you're right, of course, so that P lambda, maybe yes, intersection of this and maybe not even P lambda. Yes, of course. P lambda. You don't even maybe this condition is not even needed, right?
No, we should guarantee this is a lattice. Then it's not some sequence.
No, but if it's less than lambda,
Yes.
then it is just obtained by subtracting roots from positive roots from lambda. Then it's actually a lattice. It's not this one is not a lattice. It's a part of, but it's some discrete set.
Yes. Just
It's like an
to guarantee that it cannot
yes.
have some infinite form with the finite.
Yes. So I would rather define P lambda to be all mu that are less or equal than lambda. Right, and then intersection of P lambda with C tilde is what? So you have your lambda is something. It is sum over I from 1 to R, I don't know, some Ni alpha I, right? But then this is just all mu's such that they are of this form, right? Mi Ni minus Mi is actually integer and actually non-negative integer, right? And then Mi you also would like to be greater or equal than 0. So now I think it's clear that you have finite number of such things, right? So if you suppose you have just one simple root, right? You started somewhere in you started somewhere in positive. This is your line. This is your weight line, right? And you start, if you fix something which is greater than 0, then what it says, like in this one-dimensional example, is that there is only, you can only from a fixed point subtract finite number of, so between 0 and this one is only finite number of integers. That's what this says, right? And for two-dimensional pictures, there's only finite number of dots. Well, you just repeat this for every coefficient. Okay. So yeah. So this part is clear for me. For example, if you actually know this, right? But this one I don't know. So if you remember your solution, then you can, or some arguments, then you're welcome. Otherwise, I can tell you another solution. Okay. So then let me tell you.
And how, I want to see how it relates to the second problem.
How is it related to second problem? Okay.
And the second problem is any which subspace of a Verma module is finite dimensional. What does it mean is, let's just recall some facts. If we choose our lambda to be highest width, and these is our lambda, and this is our origin, and we have some lattice point here, and the dimension of this space is just the root from here to here, just in this surrounded area.
So dimension of the space, say it again, what?
Is the number of the that region. This is number, this is origin. And the dimension of that space is just it's for the simple roots. If this has two simple roots. And it's the number of the root that pass this point surrounded by this area. What does it mean? It's just this is one. This is one root. A root. No.
A path? You mean path?
Yes.
Uh-huh.
Yes. Here.
It's less than or equal to the number of paths. It's not strictly equal to the space.
Yes.
But it's work for, still work for you are.
Yes. Since you have finite point in this area, so you have finite path, and the dimension is less than less or equal than the path. So it has the finite dimension.
Yes, something should be said that like paths. Well, you can go in cycles, right? Like, what does it mean, path?
If you just x some e, let's say some f in this direction, and if you go up, you can never go back, and so it's not in.
All the root and not root weight is looks like this, and
Yes.
the coefficient should be positive number. So how you get some vector in this space? You just find how many ways you can minus this simple root. So that is some oriented path. By oriented, I mean you can just go by the negative direction of simple root.
You mean go from lambda
But also you can go not only by simple roots. If you can only go by simple roots, then there's only one path. There's only one way to write this thing, because simple roots is. But
that is just the angular value. But how you get the angular vector is you choose the way.
Yes.
That is not exactly the number of the dimension, but it's the upper bound of the dimension. So.
Yes, but okay. So this is problem 2. You said that it's related to problem.
Yeah, but there's still something should be clarified, because from problem 1 we get something. The result is only work for if you choose this mu to be the origin, and also you should do some work to shift this point to be any point. Because you need some volume is finite.
Yes.
Yeah, but from the problem 1 we got the reason. We got the result only for this point in 4.
Right. But what if you take lambda somewhere else? But let us finish the proof of problem 1 first. So what I propose is to do the following. Let me take our C plus bar. I claim that it has a similar description to the C tilde. Actually, we have fundamental weights, omega i's, if you remember. And then omega i's are such that 2 omega I alpha j is delta ij. Okay. So this is definition of omega i's. Then C plus is actually all lambdas in my E or whatever H star R, such that lambda, so omega i's also give me basis, and I can again decompose it like this. So how should I should in this manner, right? Lambda is Ci omega I from 1 to R, such that Ci is greater or equal than 0. So I claim that the closure of main like positive Weil chamber is exactly this set. Is that clear? So here's the definition that we had. All right. So how to prove that this is the same as this? So if I take something from this set, right, and compute so with alpha, with some positive alpha, right? So positive alpha is the positive linear combinations of alpha i's, right? So I actually can change here alpha from R plus to alpha from pi, right? So that doesn't really is the same. So I take alpha j, and so this will be Cj, which is positive. So this set is inside C plus bar. So if I take something from C plus bar, and I decompose it like that, right? And then, I mean, that thing actually says everything, right? Right. So if I take this sum from C plus bar, right, then its scalar product with alpha j is positive, but its scalar product with alpha j is exactly Cj. So therefore, this coefficient is positive. So this thing is exactly what's written over there. Now, let me now take some lambda from. So I need to so my lambda is from C plus bar. Okay, and let me take mu from also C plus bar and mu less or equal than lambda. All right, so take then I have that lambda plus mu is in C plus bar, of course, right? Just because of that. Then lambda minus mu it's sum of, I can decompose it as a sum of over alpha i's like this, where ni is actually non-negative. So ni is from z greater or equal than 0. Okay? So this is because mu is less or equal than lambda. So this is what it's just the same. And now comes very elegant trick that I like about this problem a lot. Okay, so let me erase this. I would like to compute a scalar product of lambda plus mu with lambda minus mu. This is difference of this, right? So lambda minus mu mu. Then this one I would like to decompose using basis omega I. Since this is in C+, this decomposition will have coefficients which are positive, right? So this one I can write as Ci omega I, where Ci is positive, right? But this, on the other hand, I would like to decompose using the other basis, alpha i's, also with positive coefficients. So this one is like that. Maybe I would like to write summation index here different. But then, if I take now scalar product of these two, then omega, I will have delta ij because of this omega I and alpha j here, times some constant, but this constant is also positive. It's 2 over alpha j, right? So actually this thing is sum okay, let me write it like this: Ci and j times 2 over alpha j delta ij, and ij from 1 to r. So, okay, this is a bunch of terms, but they're all positive. Right? This is positive, this is positive, this is positive. So this is non-negative, I should rather say, right? So this is, so therefore, square of lambda minus square of mu is greater or equal than 0. So therefore, if I choose mu like this, then mu belongs to the set, well, to the sphere, to the compact set that you wanted to find, right? These are all x in E such that length like of x is less than or equal than length of lambda. So this is our compact set. But also now we will need intersection of this sphere, right? I don't know, let us call it S lambda. with a subset such that of mu such that mu is less or equal than lambda. So this is of course finite because we started our discussion with that. Okay. Okay, what about second problem? In second problem, it was said that yeah, so we would like to fix some weight subspace, right? And look at this dimension. So where should I write? So maybe, so let me fix mu. It's a weight in the m lambda. So okay, we're trying to think in paths, but it's kind of still looks vague to me. Right, so what was said is, okay, we take lambda and we start subtracting, so this is some picture, like two-dimensional of what's going on, subtracting positive roots, right, and of course mu lives somewhere in here, and dimension, and we would like to find a dimension of m lambda mu. And then again, what is the statement? You're counting what?
This dimension is less than or equal to the number of classes.
So my paths. Okay. First of all, I should fix. Right. I draw an edge between 2 points. If I can go from here to here by subtracting positive root, and I draw an arrow. Right. So let me just feel like consider all possible points in lambda minus this in all points, right? In all possible ways of Verma module, and draw all possible edges with arrows. And we say that path is if we can go like following arrows, right? So this is, I guess, detailed enough definition of path. And so you count all paths like this, right? And you say the dimension of this dimension is less or equal than all paths like that, right? Which is of course true, right? Valentin, do you understand what's going on?
More or less.
Yeah, because everything is generated by the highest.
Yes, so this is our v lambda, right? It lives here. But then we start applying elements fi's. Not only fi's, but also so fi's. We can. They are all only elements corresponding to simple roots, but also you can apply f's from triples that correspond not to simple roots, but to positive roots as well. It will also give us some multiplicities as well, right? So if I can go from here to here by applying f, I can draw an arrow. And so the multiplicity, so just by PBW if you wish, right? What is Verma module? I take 1 and apply like f's in any way I can, right? And of course, dimension of what I can get in this weight space cannot exceed like the number of ways I can get vectors of such weight from the highest one. Okay, so that's what's going on, and we try to draw pictures. Okay, is it clear? Prasun? Abner? All right, so then but why number of such paths is finite though? I'm asking about any point in here, so it's not, for me it's not that clear. So you're trying to use the number 1, right? So you're trying to say, okay, let me say, take mu such that it's also in C++, and of course I have finite number of points which I can go through, so therefore I have finite number of paths. Which is also not so accurate. We gave a definition of path, but again, you need to prove that you have no cycle, so something should be said, right? Like, and obvious doesn't, I don't think it's, like it is obvious, but it's not an argument.
Because everything generated by the singular vector and the action of f is not involves the operator e, so there's no thing.
Yeah, you can again use the notion of height. So going by an arrow each time you decrease the height. So you cannot go back. So maybe that will help. But again, it still works only for mu's that are inside C++. This argument. But I would like it to be for any mu from any weight from m lambda. Well, how to do that? So this one is actually easy. We just and again it was said already. So any mu can be written like that, right? It's lambda minus sum and I alpha I. Right? Where this actually is I from 1 to R. Right? So we just take this sum here. We forget about mu and lambda, take this sum, and dimension of m lambda mu is actually exactly number of ways to write sum and I alpha I is sum C alpha alpha, where alpha is any positive root. Right? Of course, if I take only simple roots, there's only one way to write a vector like that, because it's a basis. But positive roots, I have more than needed, right? So there are different ways how I can write given vector using positive roots, right? And this number of ways is actually exactly by PBW, actually, this is exactly equality here. But we don't even need equality. We can write less or equal and still prove that it's finite dimensional. But how do I find that there is finite number of writing like that in any given vector? So any positive root, if it's in R plus, it's sum of some, B I from 1 to R. Bi corresponding to this alpha, right? Where Bi is actually lives in Z greater or equal than 0, right? So each positive root we can write like that. So you start with this. This already gives us one way to write this thing like that, right? Because simple roots are positive roots. But then you just subtract from Ni, right, something. In a way, okay, so then what you can do? You can subtract from Ni something such that what is left will be some positive root, right? This will give you different way to write it, right? So for example, if I chose some alpha R plus, right, and I can start with this one, but then subtract Bi alpha. Alpha I plus alpha. So that's another way to write this as a sum of positive roots, right? And I can start doing that. So but I can do that only if this thing is positive. So of course, so it's number of ways to write this where C alpha is positive, right? Because I go from the highest weight downwards, right? So therefore, starting with this, I can apply this operation, right? Extracting a positive root, right? Once these numbers are positive, there's only finite. So there's only finite number of ways to do that. You subtract one positive root, you subtract another, third one, and there's only finite number of ways to subtract from this sum positive roots such that coefficients are positive. And this proves this problem. Okay, so Prasun, did you understand what? Sort of doesn't work. So yes or no? No. Okay. So do you understand? Okay. Do you understand why dimension of weight space is the number of ways to write this as this? Right? This is just because by PBW theorem, you take V lambda, right, and apply Un minus to it. And Un minus has bases like that. F1 to some power k1, d to some power kd. Where f1, fd, these are all f's corresponding to SL2 triples corresponding to positive weights. Okay? So that's what how we count these paths as well, right? You take lambda and apply these f's, and that's exactly number of ways to write it like that. Now let's see how many such ways. There's at least one, right? Because alpha i's already positive, right? But what else you can do? You can subtract from here positive roots, some linear combination of positive roots, in such a way that your coefficients of the difference are still positive, because we need these coefficients to be positive. Right? And then, but there's only finite number of ways how we can do that. And so that's what's going on. Okay. So let's so 10.3, what was that about?
Calculate the Verma module SL3.
No, okay, we might skip that. If somebody wants to, we kind of did it was like a reminder from this. We did this last semester, right? So, okay. So Sanchita, you said that you have some idea about 10.4.
I mean, I didn't make much progress, but I can speak.
Okay, sure. Okay, that's. Okay. First, remind what was 10.4 about.
Okay, so the question is about SO5C, and we have to write fundamental representation for it. Okay, and
It's a pictures. Okay, you can do it completely.
I
Okay.
don't know, because I wanted some specific representation of matrices, and I didn't find it, so I.
You don't need it. So the question is to find
there
all
are-
weights in fundamental representations.
Yes.
Oh,
So we
very
have
good.
Omega 1 and omega 2, which are two of the fundamental weights, and we have this diagram for SO5, and this is okay. And let me think, what did I do after this? Okay, so it has two simple roots, and just a minute. I think in one of the ways we can write the two simple roots like this, using these from Cartan matrices.
So these are, but these are not coordinates. These are not Cartesian coordinates of roots in this picture. That's something we discussed after lecture, right? But if you try actually to take Cartan matrix and treat its columns as Cartesian coordinates of roots, you will get distorted picture.
Okay.
Like if you really try to do that, it's just because it's not. This is not how we. It's not the basis in which we are drawing this picture actually.
So it's like tilted by.
It's rescaled in some directions actually.
Okay, like in terms of angle.
No,
Or length.
angles I don't think they change. I think it's rescaled. I think it's rescaled along like a longer roots or something because of 2 over alpha I somewhere.
Okay. So,
But back to the problem. Okay, so.
So I think there is some way from this we can build the other roots, but I couldn't really process. I had read
Yeah,
about
but you need weights, right? So okay, you can totally do this. So can you please draw the root system for SO5C?
I think this is the yeah, and this is just the coordinate perpendicular, right? There are two of these.
Okay, so hint, angle between simple roots is what?
It's one root 2.
So you have two simple roots, right?
Yes, yes.
Corresponding to two Dynkin diagrams.
And I think this is root 2 because of this.
Yes, so this is a ratio between lengths, but what about
Oh,
angle?
Yeah. Oh, angle is, I think, I think this is the angle, 3 pi by 4.
3 pi by 4. So therefore, it's all happens in square. And
And the length is different.
so you have either something pointing to the vertex of square or to the middle of an edge,
I think
right?
the
So
lengths are different here.
okay, so let me. So if you draw beta, right? Then it should be at the angle 45 degrees to this one, right?
Okay, I
And
did.
nothing is here,
Oh,
right?
yeah, okay.
Yes,
This is 45.
yes, yes. So actually, your picture of root system
So we have this.
is, yes, so you have this root and this root. Like that, right? And then this, maybe this, and this.
Okay, there are 3, 6.
Right? And your simple roots are this alpha and beta. So now I would like you to find omegas.
Fundamental weights, okay.
Yes,
They
or
are-
maybe on this picture, okay?
Okay, they are the ones that is like kind of beta inverse because they give you.
So the, yes,
Let's write omega 1, comma alpha I. Okay, alpha is equals to delta.
yes, delta,
Norm alpha. Okay.
yes.
And this is 2 by our
So the,
normalization.
yes,
So and this is 2. So this is omega 1, comma alpha is delta 1 alpha.
this is not 2 for everything. This is 2
Okay.
for some roots and
Excellent.
for others maybe not. So this is true. So what you should make out of this is that your omega 1 is maybe then not alpha and beta, alpha 1, alpha 2. So your omega 1 is orthogonal to alpha 2, and omega 1 projects to the half of alpha 1.
Half of alpha 1.
So that's what it says.
Okay.
So that's how you find fundamental weights.
Okay. Let me just think. Omega 1 is with alpha 2, and omega 1 also projects at the half of alpha 1.
Yes.
So this, and it's here.
Yes.
So it is something like this.
Exactly. Exactly. So this is omega 1.
Okay.
Okay, so let us ask Abner to find omega 2. Thank you very much. Yes. Come on. Otherwise, there's no point in you being in the seminar. So we this is system B2, okay? So what are fundamental weights? So the fundamental weights are defined like this. So omega i's. They are defined like this: omega I with alpha j over alpha j is delta ij. So it's the same as written here. Alpha j, we have two of them, alpha 1 and alpha 2. Okay? So these are simple roots. Okay? So what it says, I'm translating into words. Yeah, I'm translating into words. It says that, so omega 1, how did we find it? We say that omega 1 with this number should be 0 with alpha 2. Right? So it's orthogonal to alpha 2. And it projects to alpha 1, to half of alpha 1. And then if you reverse 1 and 2, everything applies to omega 2. So omega 2 is orthogonal to alpha 1, and it projects to the half of alpha 2. So can you please find it here?
It should be omega 2, you said?
Yes.
It should be this one.
Yes, exactly. So it's orthogonal to alpha 1, right? And projects to the half of alpha 2. And it's actually for any root system, you find fundamental roots like that, right? In three dimension, if you can draw all that. So it should be orthogonal to all other simple roots, and to the root with the same index, it projects to the half. Okay. Thank you very much. So now how to find? So this is okay. What is C++? C++, where it is here?
That's
Which one? It is the convex hull of omega 1 and omega 2, as we discussed, right? So C++ is actually this, right? And its closure is this together with this thing, right? Okay, very well. So now, so this belongs to C++ bar, and it belongs to P, right? So this is some highest. So let's take the representation of this highest weight, okay, and find all possible weights in this representation. What should we use? Symmetry. What symmetry? Yeah, with respect to action of Weil group, right? So it means that, okay, I have dimension 1. The weight space of this weight is dimension 1 because it's highest weight. It's only 1. Everything else goes by n minus, is smaller weights. So then let me find its reflection with respect to S1. I need to find plane which is orthogonal to alpha 1 and reflect it. So I will go here. Then let me go and reflect it with respect to S2. I will go, so S2 is this one, right? And if I reflect, I don't change anything. I stay here. But then I can reflect this one with respect to, but then I don't even need this. So a positive Weil chamber, this one, is the fundamental domain for with respect to the action of Weil group, right? So if I take this thing and consider its image with respect to reflections, right? What's going on in this domain will give us everything, right? So its image with respect to this reflection is this domain, and this point goes to this point. Now I can reflect it. So all these things are Weil chambers between these two lines, right? And corresponding points are these points. So this is an orbit of this point with respect to action of L group, right? So all these weight spaces are there, and they are of dimension 1. And there are no others, by the way. Why? Because you take this one, its highest, and then you subtract roots. If you subtract any root, I give you this particular weight just because if you subtract any root, you go outside of well chamber. Okay, but well chamber kind of gives you everything. So this is the only point in well chamber. This is the only point in well chamber corresponding to the weight of the subspace, right? So for example, if I subtract this root, I go here. If I subtract this root, I go to here, outside of well chamber. Okay? So this is the only point of fundamental representation with this highest weight, omega 1, that lives in C plus bar. And then I take this point, reflect it, and this will be all the possible weights, and they're all of dimension 1. So this is a picture of fundamental representation, first fundamental. Now, can anybody draw points for the second one? So we figure out that omega 2 is this one. Omega Sanchita, maybe you can. It's similar, but not the same. Now your highest weight is this one. Okay, so you have this one. Then what are other points? Please. Come on.
Okay, before we had this and we were reflecting.
So what was the argument? This was the only point in here of this representation.
Yes.
So can we check the same thing for this one?
We reflect along this.
Yeah, you can reflect first. Yeah, sure. Yes, very good.
This point.
And two more, right?
Yeah, I think
This one and this one. Yes.
So
That's it, right? These are all. So you see, these are all. These two Weyl chambers, they share this one. These two share this one. This one. So you kind of. So the only thing to check is that this is the only point in C plus bar. But again, you subtract positive roots. If you subtract this one, you go to this point outside. Then you subtract which one? This one, you go also outside. That's it. So these are all. So blue dots are all weights in second fundamental representation of SO5. Okay. Okay, 10.5. I promised this on the lecture. So okay, let's do this if you have time. Yes.
So here, like we have 4 in each representation.
Yeah. So these are two different representations. Yes.
It's like how do we get a 4? Just by saying we are in SO5, and of course we have 2 of the simple roots that we know.
Mm-hmm.
Just from that, can I make a statement that there would be like a 4 roots in the fundamental representation?
For weights, you mean?
Yes.
No. It's just you just look at the pictures, try to reflect, and see that you have four. Actually, it should be like that. If you are on the boundary of C+, then you will get. Well, then you can say something about orbit of the action of Weyl group. If you're on the boundary, you will have 4 points in the orbit. It will be order of Weyl group divided by 2, because one reflection doesn't do anything. If you're inside C+, then you'll have 8 points actually. But this is only about orbit of a highest weight. It might be something inside as well. If I take like some point here, I subtract a root, I still get something in C+. and I have more points inside this outer thing.
Okay, so basically.
So yeah.
I'm just trying to understand, for example, when we have simple roots and, the basic roots, simple roots, and at that time we have, just by looking at a group, we can make an understanding that, let's say for SLN and all, how many simple roots are there, but we cannot have such a thing for the fundamental representation.
No, you just take, like, you go case by case.
Okay.
You can try to construct it from Verma module, for example. Yeah. But these two representations are very simple. So you just use symmetry, and like there's only one point in the C++ bar, and that gives you everything in this case. So I take lambda from P+. I would like to act by SI, shifted act, on lambda. So I will try to be quick. I don't know how much time is left. It's okay. So no time, but I will try to be quick. Okay. So it means that I take lambda plus rho, apply SI, minus rho. Right? It means that actually, so let me skip computations and say that this is actually I have this number lambda of alpha I, and it is integer, it's positive integer because lambda lives here, and it is exactly weight of V lambda, which is highest weight in here, with respect to action of SL2 alpha I. So this is highest weight with respect to SL2 alpha I. All right. So this is actually, let me denote it as lambda I. Lambda I, negative lambda I minus 1. So this is some computations, and well, you maybe I also should say that well, okay. So then some technicalities. So I suggest you to check this. Okay. Now the point is that I take V lambda. Then if I apply to it Fi, like some multiple times, and consider all these vectors, this gives me a Verma module for SL2 alpha I. So this is Verma module for SL2 alpha I. But in Verma module for SL2 alpha I, what's going on? Let's recall. We have highest weight, lambda I in this case, and then I go by 2, applying Fi. And if this lambda I is positive and non-negative integer, then what happens? If I go to negative lambda I minus 1, then going back I get 0. So then Ei here goes to 0. So this is just representation theory of SL2, right? That's how we actually created like the. So again, this is from the previous semester, right? If you started with something integer non-negative, then on the level negative lambda I minus 1, you'll get singular vector. But this is exactly the weight which we got here. So we started with some lambda I, applied. So let me just take vector fi lambda I plus 1 applied to v lambda. So this is my vi that we had in lectures. Right? From the representation theory of SL2, I know that ei applied to vi is 0. Because I go back in Verma module for SL2 alpha I get 0. But what about other ej vi's? So ej vi, I also would like it to be 0. Why is that so? It's just because ei commutes with fj. If I and j are different indices. We had this one of the Serre relations, right? So therefore, vi, this is the definition of vi, right? So I take ej, apply it to fi lambda I plus 1 times applied to v lambda. ej commutes with fi, and his v lambda. V lambda is singular vector, so therefore I get 0. So this is the same as fi to lambda I plus 1 ej v lambda. But this one is 0. And this is because fi commutes with ej. So therefore this happens. ej vi is also 0. So therefore vi is a singular vector. So it is singular. It is killed by ej with different things. For this very simple reason. And it's actually it happens for all elements of such sort. If you take v lambda and apply fj any number of times, right? But you also need ei to kill it. And there's only one point where it can happen. All because lambda lives in p lambda. Lambda lives in p plus, right? And this point is exactly this very important point for representation theory. So that's it. So if this technical step will be not clear, just let me know, we can do it.